able to use data week mechanism for supporting, oh, hang on, I need to do that. There we go. Supporting the CDTs and the student cohorts within the CDT. So this is the second of 3 seminars that we're running this morning, focusing on the CDTs. This one is Compass. We've just really enjoyed digital health. And I'm just going to take the opportunity very briefly to introduce the JGI for those of you who don't know us, so that hopefully you'll be able to make the most of the opportunities that we, oh, I've lost, hang on. Thank you, that's great. So that you can take any opportunities coming up to kind of contact us or take up our funding opportunities and that kind of thing. So this event is on day 5, the last day of University of Bristol Data Week, which is a series of events that we run in the second week of June every year. We have done for 5 years now, and I'll show a slide in a moment that shows you the kind of things that we do. But the reason we developed Data Week a few years ago is because no. How do I move it on? No. Sorry, unfamiliar system. Are you controlling that?
I think Karina might be.
Karina's controlling it. Okay, right, great. Thank you. Is because we're the University Research Institute that's tasked with supporting data science and AI across the university. And just for those of you who don't know, as an introduction, we actually have 4 key priorities, which are represented here on this infographic as the verticals. So those are data challenges around kind of societal benefits, societal challenges, data visualization, which actually is broader than that. It includes materialization and kind of realization of data communication and data journalism as well. We have a thread around reproducibility and data governance, and that includes everything from kind of data hygiene and how to clean data through to legislative landscapes, consent and ethics issues as well. And of course our foundational or fundamental research, which at this university is largely found within mathematics and computer science, but actually there are pockets of really great research going on across the university and all the faculties. And we deliver these aspirations through a series of cross-cutting mechanisms, which you can see here as the pink arrows, horizontal pink arrows. So firstly, by putting on development opportunities, developing communities, events like this, essentially. Secondly, we run training opportunities throughout the year. So obviously in Data Week, we do that in a concentrated way, but through the rest of the year as well, we put on training often in collaboration with research communities, specific research communities or faculties who are interested in working with us. And if there is something that you feel would be useful to develop some training opportunities for you, do let us know, because we're always looking for new partners to build, because we're here to serve the community of data science and AI within the university. So we're really interested to hear your feedback, whether we deliver the right things, where the gaps are. We're the portal for the Alan Turing Institute, which is the National Institute for Data Science and AI. I'm the Turing University lead on that, and I'm also the chair of their Research and Innovation Advisory Committee. So I'm involved in leadership at the national level as well. And the last, in some ways, most exciting ways in which we engage is through our Ask JGI service. So this is our surgery service where anybody can contact us on Slack, on email, or old-fashioned phone, pose a data science query to us. We then triage it with our team, which is a combined team, a kind of multidisciplinary team from the institute and the wider university. And then we will get back to you with hopefully with a solution. If not a solution, then a plan. And some of the most interesting projects that we've then gone on to be involved in fact, have developed out of Ask JGI. Thanks, Queen. If you could move the slide on, that'd be great. This is really blurry slides. I'm not going to dwell on that. It's just to say that we have this interactive tool for Bristol Data Week, which allows you to have a look at all the courses and networking opportunities that we presented in the week. We're now on day 5 on Friday, and we've got a couple of activities still going on, training activities, and a really fun film prize that I'll come to in a moment. If you could do the next slide. Nobody could read that one. And this is just an opportunity for me to say thank you to all our sponsors and collaborators that make Data Week happen. So there's some really long-standing partners there, like LV General Insurance at the top. There are some new partners there, like Roche, with whom we're just starting to develop training and research programs. But the input of all our partners are really appreciated. We wouldn't be able to do it without you. Next one, please. And then finally, this is the last event of our Data Week that you might find fun. So for the last couple of years, we've sponsored a prize for the best short film about data science and AI, which is part of the Bristol Science Film Festival, which is going on at the moment. And our event is at 3 o'clock today down in the watershed. We're going to do a screening of the shortlisted films and then give the prize. And I think it's going to be a really nice event to end off Data Week. And there's going to be lots of multidisciplinary communities there. So now I'm going to hand over to the speakers. Who is first up?
Hi, Sam and Dom. Have you decided who's going to go first for us? We've got 2 speakers today from the Compass student cohorts who are going to tell you a little bit about their research. But if anybody wants to know any more about the full sort of comprehensive section of research that we do within Compass, we have a blog on our website. So please go on there. There's a monthly student update and details about each of their individual research projects. If you want to know more, please do check out our blog. Sam, can we nominate you to go first?
Well, I don't mind going first unless,
fantastic,
unless
thank you.
Want to, Dom. That's fine with me. Okay. So can everyone see me and hear me okay? Well, so I'm Sam. I'm from the 2nd cohort of the Compass CDT. So that means I've done the first year, which is the taught aspect of the CDT, and I'm coming up to finishing my first year of full-time research. And my work is sort of in trying to bridge the gap between advances made in the sort of field of machine learning and applying it to the problem of earthquake forecasting. So I work jointly with Dan Lawson, who's based in the maths department, and with Max Werner, who is based in the School of Earth Sciences. So it's an interdepartmental project, which I find quite exciting. And yeah. So I'm going to briefly introduce what I mean by statistical seismology, and then go on to talk about ways in which we can do statistical seismology through the lens of these models called point processes. And then I will talk about some experiments that I've conducted on some synthetic data sets and on some real ones as well. So for quite a while now, seismologists, so people who study earthquakes, they've been trying to understand the kind of underlying physics that goes on beneath our feet when earthquakes happen. And they've simulated earthquakes in the lab by like putting rock under great amounts of force, or they've tried to like map out the fault lines between tectonic plates. But any kind of earthquake forecasting model based on these gets regularly kind of outperformed by models that are based on just looking at the distributions of earthquakes, the times of earthquakes, where they're located, and and the magnitudes as well. And so that is kind of what statistical seismology is. It's thinking about earthquakes in terms of statistics and probabilities and distributions. And one of the most popular ways of doing this is through what are known as point processes. So point processes consider earthquakes to just be, rather than thinking about a fault line, they think of earthquakes to be points in time and space and having magnitude. And sort of for the rest of the talk, if we'll just imagine that we're not going to think about where they are in space, but we're just going to try and predict the points in time when earthquakes are going to occur, but we'll also think about their magnitude. And so the kind of models that model these kind of processes are known as temporal point processes, and they basically generate these random discrete points in time, so random times ti, and also with magnitudes. And the way they're parameterized is through what's known as their intensity function. So the intensity function at time t is the probability that there's the probability of there being an earthquake in some small interval about time t, conditioned on the history. So that's conditioned on all the times of the earthquakes up before time t. So one particular model, the sort of most popular one, is known as the epidemic type aftershock sequence model. And it assumes that we have some constant rate of earthquakes, and then the rate of earthquakes is made up of a contribution of summing over all the earthquakes prior to time t. And this is a function with parameters, and in trying to fit this model to data, what we'll do is we'll try and maximize the probability or the likelihood of observing a sequence of times of earthquakes. And through maximizing this function numerically, we can infer the parameters of the intensity function. So my work, instead of assuming this kind of functional form of the intensity function like ETAS does here, instead we're going to try and construct a really flexible model for the intensity function. And the way we're going to do this is through neural networks, as they're known as good function approximators. They're very flexible to fitting observed data. But we're not going to directly model the intensity function through a neural network. We'll first make this modeling choice that the intensity function is equal to some function of the time since the last event. So if Ti is the last earthquake before time t, and it will also be a function of this vector Hi, which will be some approximation of the point process, but I'll get to that later. And then what we'll do is we'll let this capital phi, which is the integral of this little phi, we'll let this be the output of our neural network. And what we see is that when looking at the expression for the likelihood again, where this is log of a function minus the integral of a function, in defining phi in this way, it means we can re-express this as sort of log of the derivative of a function minus the function itself. And so in doing this, we sort of navigate around having to calculate the integral of this function, which we might not be able to do, but instead we can reformulate it as the output of a neural network and the derivative of the output. And because we can easily calculate derivatives when applying functions within a network, we can easily sort of and efficiently calculate this derivative. And again, through maximizing this function, we can find the parameters in our neural network and come up with a new flexible model for point processes. So what we can do is we can test this flexible model for point processes by simulating some data from the ETAS model. So that's the existing model for earthquakes. And what we find is we can plot the intensity function, and we sort of see that the intensity function can approximate the ETAS one rather well. So this is pretty promising, but what's most promising is the fact that the time it takes to train, so that is in maximizing the likelihood, the time it takes to train the neural model is far better than training the ETAS model. Now, if we go back to the expression for ETAS, we can see that the intensity function includes this sum over the past events, and the likelihood as well includes summing over all events. So it means in evaluating this function, we have to compute a double sum, which means that as we increase the size of the data set, the time it will take to train this model will grow as a sort of function of n squared. Whereas for the neural model, this only grows in the order n. So as data sets get bigger, it makes much more sense to be using this model as it's much more computationally efficient. And the reason we can do this is because, going back to what I mentioned before about we're approximating the history of the point processes with this vector hi, and instead of having it depend on all of the points before time t, we let it be, we learn an embedding of only the last d events. So this improves the computational efficiency. So the next thing we can look at is there's a series of, well, 4 really big earthquakes that happened in central Italy, and I think it was across the space of about 6 months in 2016, and it was really destructive. I think about 300 people died, and the estimated sort of economic damage was between like 1 billion and 10 billion. So it was really destructive. But at the time, there was a data set created for this sequence, and because earthquakes generate waves, and initially the data comes through in these sort of waveform format, and what someone has to do, human has to look at this data and label the points and say, yes, this is an earthquake here. And so that was how the original data set was created. But more recently, so about 3 years ago, somebody automated this process, and so they trained an algorithm, a classifier, to label and classify that when looking at this waveform, that they can say, yes, there's been an earthquake here. And so what that meant is that this, it sped up the process a lot, but it also meant that earthquakes of much smaller magnitude could be added to the data set. And so the newer catalog, the data set for earthquakes that was created from this, went from being about 90,000 earthquakes to 900,000. And so this is what the data set looks like. And what this red line here is an estimate of how much of the data we believe is missing. So what happens is when there's a big earthquake and the ground's shaking so much, we can record the smaller earthquakes, which are kind of happening at the same time. Our ability to record them is much worse because all the instruments are shaking, and our reliability of recording these small ones is much worse. And so we can see that, and this line is an estimate of the earthquake magnitude above which we believe that we've got all the data. So below this line, we believe that there's some missing data points. And we can see that at the times of the really big earthquakes, this line, it shoots up a lot. So the times of the big earthquakes, we've got missing data. Okay, so going back to our 2 models, we can compare them against each other. So there's the original ETAS model and the neural model. And from this data set, what we can do is we can pick a point in time. So it will be just before this large earthquake that hit the Viso region. We can use all the earthquakes up to that point to train our models, and then use the remainder to test the models. And what we can do is look at a performance difference in the 2 across the testing period. So this is a sort of cumulative difference in performance of the 2 models. So it's the performance of the neural model minus the performance of the ETAS model, sort of cumulatively summed across the testing period. So what we notice is that this is all positive. So the neural model is performing better. But what's more striking is the fact that the times at which it's making the biggest gains, so these sort of sharp jumps up in performance, are exactly at the times where the data is most incomplete. And so what this means is that this neural model that we've constructed is more robust to the fact that we have missing data in our data sets. And one way to think about this is the fact that when we specify the original, the ETAS model, what we're doing is we're specifying what we believe that the actual ground is doing beneath our feet. And so if we try and fit a model to just the observed data without some of the data points, then we're going to have model misspecification and we don't fit it as well. Whereas when using a really flexible model, because we're just fitting to the data, we're flexible enough to just learn how to model the data that we observe rather than the actual data that's being generated. And so that's why we're able to make these gains in performance. And so in constructing these sort of more flexible point process models, we're able to construct something that is more computationally efficient than the original model. So particularly if these data sets are growing, this is going to be much more useful. But we're also able to construct a model that is more robust to any missing data points that we have. So thanks very much. Is there any questions?
I have questions then for Sam. Oh, and Dom has appeared. Dom, do you have a question, or are you just lining up your talk to start now?
I have one question I've been thinking about since I saw this talk last. So there's some advantages to using the neural network.
Yeah.
You talked about, you've outlined.
Mm-hmm.
They are quite expensive, from what I understand. Is there any advantage to using those as compared to any other non-parametric regression method? So like basis sparse or Gaussian process.
So there's neural networks and there's neural networks. There's neural networks that are these big multi-layered convolutional nets that try and classify images for Google, whereas this is a really quite small, not very deep, not very many parameters to learn. And so this one particularly isn't actually that expensive to use. Yes, definitely there are other non-parametric methods out there, but in using those, we still have to express some sort of like dependence relationship between maybe like the history of past events to future events, and through using this model, we can learn that dependence as well. But I haven't personally explored any other non-parametric methods. But in using this, it's almost, well, in some ways it's cheating a little bit because we can kind of automatically learn the right kind of dependence on the past. Whereas I don't know if that's always possible with other non-parametric methods.
So do we have bad information about what these relationships look like, and is that the strength of the neural network?
Well, we have our information is, and what we believe is that there is a sort of a contribution from all the past events, or there is a contribution from the past, but when and we believe ETAS is a pretty good model for it, so summing over all the past events. But in constructing a model that's only based on the past D events, we can learn how these past D events will be, they'll be expressing some sort of behavior that will be dependent on the events that preceded them. So we can navigate having to explicitly visit each one of the past events and show how it contributes to the next one. But we can look at the most recent ones and use that as a predictor.
Okay, that's very interesting. Thanks, Sam.
Yeah, no worries.
Sam, yeah, we've got a question in the
There's
chat for you.
Question in the chat, yeah. So the question is, what kind of neural network do I use? So there's kind of two things I talked about here. There's one is this learning approximation of the intensity function. So that is done through the sort of most basic feed-forward neural network. But the other thing I mentioned was learning how to embed the last d events before time t, and that is done through recurrent neural networks. So the data gets fed into a recurrent neural network section, and then out of that we get fed into just a simple feed-forward neural network. Thanks everyone for my talk, and I'll hand over to Dom.
Cheers, Sam. Dom, are you ready to go?
Almost. Let me put this in full screen. Okay. Can everybody see this in full screen?
Yes.
Excellent. Okay. Thanks very much for coming. Thanks for inviting me as well. So today I'm going to be talking about change point detection, Lasso regression, and the climate crisis. So this is one part of my thesis. She's almost done, I want to say. It'll be appearing on archive soon. I'm working generally on change point detection with my supervisor, Hayron Cho. So I'm going to start my talk today with a quote. A wise man once said, "Well, the times there are changing." This is kind of a defining theme of everything I work on. Hopefully you'll understand what I'm talking about by the end of this. So why do we care about data segmentation or change point detection? So time series models in general assume that the underlying dynamics of an observation series don't change over time. So we collect a lot of data, and historically what we do is fit the model to it, assuming that the behavior of the world doesn't change. In reality, that's not what happens. In all of statistics, we make simplifying assumptions, and this is a potentially dangerous one. Most of what I work on is data from finance. So, for example, if you try to fit some sort of returns forecasting model over the last 20 years, you'd be fitting data over 2 or 3 financial crises. Your predictions wouldn't be very good, neither would your inferences. What I'm talking about today is an application from climate science, but similar methods are used in genomics and neuroscience. So our approach to non-stationarity in time series is to assume that, quite simply, the dynamics are in fact stationary, not changing between some unknown change points. So the model performs normally until a certain point. Behavior changes abruptly. So in a parametric model, the parameters suddenly change. The problem for us is to detect where these change points are. So this is useful for forecasting. So in the returns forecasting example I was talking about, your forecasts will change depending on the model that you fit to each stationary distribution. And you can interpret what these change points mean. So if you detected a change point in a time series, you might correspond that to a certain event. That's not an easy thing to do though, so I'll speculate about that later on. So perhaps the simplest possible example of a piecewise stationary model is this one. So we model the data as piecewise noise around a mean. So until time 50 here, we've got observations with mean 0. On this segment here, we've got observations with mean 10, and here observations with mean, I think this is 9. So you can see this change here, you can tell that by eye. I could look at this and say there's a change point there. if I just saw these black observations, I might struggle to tell you this one's there. The problem for us is to identify these two change points here and possibly identify the model in between. Sometimes we're interested in that as well. This very blurry picture is some observations of yearly recordings of discharge at the Aswan Dam along the River Nile. So around here, I think this is maybe 1905, the Nile Authority built a dam at Aswan, which you might expect to cause some sort of sudden decrease in the volume of discharge. But any sensible change point detection methods will tell you there's a change point just before when the dam went up. And you can correspond this to rainfall observations they have in preceding years. So we've gained some insight from applying a change point detection method. We've learned something about the state of nature. The approach that I work on is the MOSUM approach. So this is a sliding window method for estimating the locations and number of change points. Basically what we do is we take candidate change point K, you calculate the average to the right-hand side and to the left-hand side over a certain bandwidth G, and you compare the two in terms of their size. So you'd expect that when data is stationary, the average on the right-hand side and the left-hand side are going to be very similar. So this detector, the absolute difference, it's going to be really small, which you can see here. So this is me applying the MOSUM procedure to this data set here. We can see that this large jump here, there's a large detector value, and at the small jump at 150, that's a very small detector value, but we still detected both of those. So we can use local maxima as change point estimators for the number and location. So that's in the univariate mean plus noise setting. That's a really simple setting that isn't super appropriate for every kind of observational time series that you'll have. Occasionally what we'll get is observed pairs YT and XT. So we're observing one time series and a whole load of other time series, and we're interested in modeling one time series based on the rest of them. We want to predict this and do inferences about YT, and we'll model the relationship as linear. So this is the inner product of XT and some parameters plus some noise. What I've been working on is sparse regression. So traditionally, back in the 1900s, 1920s, P would be small, maybe 5, and the number of observations that you have is much, much larger. Today, the opposite is the case. So we have tons of ambient data collection occurring and comparatively little data, say from click-through on social media or incredible numbers of assets available in finance, for example. So we want methods that work here. Traditional methods don't work. One thing we can do is assume low-dimensional structure on our parameters. Perhaps the most successful way over the last 20 years of doing this is to model data as sparse, which means only a few of the entries are actually contributing anything to this prediction here. So an adaptation of the model that we're working with previously, the piecewise mean plus noise model, is this. So within each segment, the parameters of the regression I described change. So beta 1 describes the regression relationship in segment 1 before change point K1. Parameters beta 2 describe the regime between K1 and K2, and so on. So we've got Q+1 regimes. To use the MOSUM approach here, we can't do what we were doing before, just averaging a series. We have to obtain some sort of implied series. So what we do is obtain parameter estimates across a sliding window using Lasso. So this is an incredibly successful algorithm for estimating sparse beta parameters. Effectively, we minimize this regularized loss. So this is the least squares or residual sum of squares, and this is a penalized term, which includes the one norm of beta. So this is the sum of the absolute values of the beta parameters, which effectively describes the size. So we obtain these over the same sliding windows that we had before, and we compare them in the two norm, which is the sum of the squared elements. And that gives you a detector that looks just like this. So we can do the same thing. We can refine, we can take local maxima as change point estimates for the number and location. If you do theoretical analysis of this, you'll find that that's not the optimal way of doing it. So the estimates that you'll get depend on local quantities that we don't want it to depend on. What we do is something I want to describe as quite clever, and we take two of these estimates that we already have, we plug them into a comparative prediction loss, either side of a candidate change point that you've already obtained from these local maxima. So we take these, you obtain parameter estimates from maybe over here and over here, you plug them into another loss, and I'll get you a better estimate of where this change point is. And that's really cheap to do, because we've already got these parameter estimates. That's sublinear in cost. So in general, our method is way less complex than all the competing methods that exist. We don't even need to evaluate all those detectors at every single point in our set. We can just use a coarse grid, which means the cost is 2 orders of magnitude less than all the competitors, as far as I can tell. We obtain the optimal detection and localization rates, as I was saying, and in practice, it's way faster in runtime, and it's at least as good at estimating change points. What can we do with this? So I had to look quite hard to get anything that makes sense from this model. It's not a super intuitive model, but one thing I did find was successful is modeling the sea ice extent in the Arctic. We know that this is a non-stationary series. People have studied this before in different ways using different models. We can see that there are change points in however you want to describe it. So we know that the Arctic sea ice extent is retreating. This is like defined as the amount of land that's covered with at least 15% sea ice. This is important because it influences the ecosystem of the area. We can model this as a dynamical system. So we'd have the sea ice extent itself. If we take the first difference of that, we call that YT. And we'd model this by trying to predict it with, say, weather covariates, land mass, wind directions, things like this. And that means that our dimension P can be absolutely huge. There's loads of things that we can use in this dynamical system. And as I was saying at the start of the talk, this piecewise stationarity assumption is really useful and interpretable, because this means that if we detect a change point, we know that the behavior of this dynamical system has changed exactly there. You can try and correspond this to, say, human activity. If we apply this to the series, so this is not the difference series. This, what you're seeing here, is a monthly adjusted series describing how the sea ice progresses over time. I think this is in one particular part of the Arctic. So you can see that a piecewise univariate mean plus noise model wouldn't be very good here, because you've got this sort of curved structure here. Plus you'd be throwing away a load of information that you have from the covariates. We can see that the behavior does seem to shift between these estimated change points here, these 3 red lines that the algorithm that I've just described estimates. And you've got these very interesting 2 sudden ones, and these have been found in other analyses of similar data. So something happened around 2007 to 2009 in terms of the sea ice extent that we don't quite understand. And our algorithm confirms that if you're modeling it as a dynamical system, the same change points exist. Someone who knows more about Arctic sea ice could probably find out what's going on there. And that's the end of my talk. So thanks very much for coming. Are there any questions?
Any questions for Dom? Questions in the chat box? There's a question here from Laura. I was wondering how you picked the thresholds.
So I picked the threshold. Okay. So that the threshold is this line here, the blue line. In simpler settings like this univariate mean plus noise setting, you've got asymptotic results that suggest where they should be. So the same as in like Gaussian tests of differences in mean, you'd get a suggestion of a threshold there for a test statistic for the log likelihood ratio. We can't do that in the setting that we're working in because P is so large. And there are a load of complicated quantities that the threshold would depend on. What we can do is cross-validation for determining what it should be. So we do sample splitting, we take every other index on the time series, and we take these candidate change points that we've generated. So grab these 2 points. These have an ordering because the detector values provide an ordering. So we take the one with the largest detector value, and we fit a model with no change points, a model with just say this change point here. So piecewise stationary to the right and to the left of this. And we compare that to the third model involving all 3. So piecewise stationary along each of these 3. And we compare the prediction loss on the unseen data. That works really well in practice and it's surprisingly cheap. So that's what makes this sample splitting is what makes the competitors so expensive. But we've done it in a really clever way. That means it adds effectively no cost.
I've got a question, Dom. I was wondering, sort of, how challenging is it when moving to time series of sort of more than one dimension, or is it simple to do change point detection in that kind of space, or do you have to do like completely different methods?
It makes life a lot more difficult for sure. It normally involves some sort of assumption on dependence between the variables. So you could say if you had multiple means that you wanted to estimate change points in, that's still like a low dimensional problem because you're not modeling dependence between the two. If you want to do, say, changes in the covariance, then your covariance is going to grow in dimensionality quadratically with the number of series you have. You have a problem with degrees of freedom where when you're using these restricted windows, you're effectively reducing the sample size massively while you're still wanting to estimate something potentially quite large. So what we normally have to do is make some sort of low dimensional assumption. So that's the sparsity assumption I described here. That works really well here. So this is effectively still like working with a low dimensional or lower dimensional series. So if the intrinsic dimension in the sparsity is, say, 5, it doesn't matter how big the parameter vector actually is, if only 5 of them are contributing to the prediction itself. So we can make some really clever simplifying assumptions to make our life a lot easier.
Thanks, Tom. Are there any other questions for Elaine, Tamara? Is there anything else that you need from us today?
I just wanted to take the opportunity right at the end to let everybody know that this year we ran a seed corn funding pilot for postgraduate research students, and we awarded 5 for interdisciplinary projects. All they needed to have was a data science, AI, or data intensive research thread, and we think it went really well. So we want to do that again next year. We haven't exactly decided the call structure, but if we worked on the basis that this year functioned fine, that would mean a call in February. So just bear it in mind, sign up to the mailing list, and then you can get all the information as soon as we have it for you. And thank you, really, really interesting stuff there. And the application area is fascinating as well.
That's great. Thanks, everybody, then.
See you soon.
Thank you.
Yeah, thanks everyone.
Thanks.